previous lecture, we established the link between the eigenvalue locations of A matrix and the behavior of the state transition matrix, namely A to the K in discrete time. In this lecture, we will do the same thing for the continuous time case. Before that, let's apply one of our findings from the previous lecture to the discrete time example, namely observer design. Suppose that we have some plant that we model through a discrete time system, modeled in discrete time. X plus equals X, Y equals Cx. This is our plant. This is the state of the plant, and this Y is the output that we take from the plant. So what we want is, because we want to make certain decisions regarding our plant, and for that we need the state information. Obtain solution X of K. Okay, solution of the plant. The constraint under which we have to achieve our goal is the following. We cannot measure X directly. Okay. So the entire state information at any given time is not available. The only available thing, or only available measurement, is represented by the output here, Y. We have to do what we want to do through the output. In other words, we have only access to the output Y. Now, if we achieve this goal under this constraint, usually what we do is we construct an observer if certain conditions are satisfied. Construct an observer. And what an observer does is, first of all, it's a system. It's a discrete time system. Unlike the actual plant, which is there in the real world, the observer system runs in our computer. Okay. And it's again a discrete time system. This plant doesn't have any input, but our observer will have an input, and that input will be the measurement that we collect from the actual plant. So our observer, which is a discrete time system, as we said, will have a state, and let's denote that state by X hat. So observer state X hat is in Rn. By the way, X is in Rn, let's say, and measurement is in R, let's say P. Okay. Observer state is X hat, and observer dynamics has the following form due to David Wilberger. A X hat plus L Y minus C X hat. Okay. And this system is running in a computer. Okay. Again, it's a real-time system. Its state is X hat, and it has an input that's driving it, and that input is the output that we collect from the actual plant. Okay. Now what we want is, we want this dynamics to produce an estimate x hat, regardless of the initial condition of the plant and regardless of the initial condition of our observer, such that this estimate becomes better and better as time goes on. In other words, x hat of k, the solution of the observer system, should converge to the solution of the plant. Excuse me. Okay, so what we want is, we want the estimate to converge to actual state as time goes on. Now what we do is, using this observer dynamics, this construction, what we do at this point is we choose L carefully so that this goal is satisfied. Okay? And now let's talk about what it means to choose L carefully, or in a smart way. Choose, and that choice may not always be possible, but suppose that the conditions, certain conditions are satisfied, and we can do this. We can go with this choice. Okay, choose if possible to observe again. L, it should be in where. Now here we have y. Y is vector in Rp, and here we have x hat, which is a vector in Rn. Therefore, this gain must convert a vector in Rp to a vector in Rn. So that means the size of L should be n by p. N by p, such that all the eigenvalues of matrix A minus LC. Now that L is n by p, C is p by n. Okay? Therefore, L times C is n by n. Hence, this difference is valid subtraction. So both A and LC are n by n matrices. Okay, all the eigenvalues of this matrix A minus LC will satisfy the property that their magnitudes are strictly less than 1. In other words, they all lie in the open unit disk, the complex plane. Okay. Now this choice, or this suggestion, at this point, if you're not familiar with observer design, seems arbitrary, okay? But it turns out that it's not, and it's easy to see that it's not, and let's do that now. If you do this, if you choose an L such that this is satisfied, and one way, it's a sufficient condition for being able to make such a choice is that this system is being observable. Okay, we're going to study that later in our course. But for now, suppose that necessary conditions are satisfied. We have necessary conditions are satisfied, and we can choose an L that satisfies that condition. All the eigenvalues are with strictly less than 1 magnitude. Now, if that condition is satisfied, then it turns out we achieve what we want. That is, the estimate converges to the actual state. And let's see why that is the case. Okay. We achieve our goal, that is, the state catches, the estimate catches the state as time goes on for all initial conditions. Okay. Now we have two separate systems: the actual plant and the observer system. That means we have a pair of initial conditions. One initial condition is determining the starting point of the blend, and the other initial condition determines the starting point of the observer. All initial conditions, x0 and x hat 0. Okay. Now let's prove this claim. And the proof turns out to be quite elegant. Define a new vector, which we will be calling error, understandably, because it's the difference between the estimate and the real value. Okay, so the difference is what we're calling the error. And once that error vector is defined, we start analyzing its dynamics. Okay. So the next question is, what's so-called error dynamics? For this, what we will do is we will obtain a difference equation that describes the evolution of the error. In other words, we try to figure out the right-hand side of this equation. E plus equals what? E plus, by definition, is x hat plus minus x plus. Okay, this plus notation simply means the value at the next time is. Now, we know x hat plus, and we also know x plus. X plus is here, x hat plus is here. So let's place these pluses, x hat plus and x plus, with the right-hand sides here and here. So what we have is a x hat plus l y minus c x hat. So this is x hat plus minus x plus, and x plus is simply ax. Now that equals what? That equals ax hat plus. Now what y is c times x. Okay. Therefore here we have cx minus cx hat. So both x and x hat are being multiplied by c. So that means we can take c outside the parentheses, and we have lcx minus x hat minus ax. Then here we have ax hat, here we have minus x. That means we can write those two terms as a single term, that is a times the difference, plus lc x minus x hat. This whole thing we can write as something times x hat minus x. That something is no other than the matrix whose eigenvalues we were careful to choose to satisfy this problem. X minus x. And that equals a minus lc times, since this is no other than the error, we have e. E plus, the evolution of the error does not depend individually on both x hat and x, but only depends on the difference. And the difference is error itself, hence the error dynamics, or the evolution of error, depends only on the initial condition of the error. Now, since we have the error system, e plus equals some matrix times e, we can easily write the solution in terms of the state transition matrix, which is no other than this matrix raised to the power k. Therefore, solution for the error system is a minus lc raised to the power k times initial error E0 for the time discrete time 0, 1, 2, 3, 4, and so on. Now, from the previous lecture, we know that since the eigenvalues of this matrix, this matrix A known as LC, all satisfy that condition, okay, they're on the open unit disk, state transition, the corresponding state transition matrix should converge to zero as time goes on. So that means no matter what the initial error is, since this matrix is converging to zero, the error must converge to zero as k goes to infinity. And error converging to zero means except and x becoming more and more equal as time goes on. In other words, our observer works. Our estimate catches the actual state as time goes on. Now, since eigenvalues of A minus LC matrix satisfy this condition. Later we are going to call this condition the stability condition for the discrete time system. We can write A minus LC k goes to zero as k goes to infinity. That means e to k goes to zero as k goes to infinity, regardless of the initial error, which depends on the initial condition for the observer and initial condition for the actual time. And finally, error conversion to zero means that these two signals are getting closer and closer to one another exponentially. X at k converges to xk as k goes to infinity. So that's the end of our proof of our claim. Finally, right? We eventually obtain xk, the entire state information, without directly measuring all those individual state variables. All we need is just a few sensitive information coming from the output. Okay, and then by looking at that output, by using that output as an input to our observer system, we generate an estimate, and that estimate becomes more and more successful as time goes on. By just measuring the output. Okay. Now let's move on to the question which we asked and answered for the discrete time case. Now we're going to do the same thing for the continuous time. And our question is this. E to the AT goes or behaves in what way as t goes dt. So we will try to answer this question from the point of view of the eigenvalue locations of the A matrix. Okay. Remember that e to the AT is state transition matrix for the continuous time homogeneous equation. Okay, x that equals ax, and the solution is x of t equals state transition matrix times the initial condition x. Okay, t is our continuous time variable. Again, we will obtain the answer to that question through the Jordan form of A. So we begin answering that question by writing this series definition of state transition matrix. Now that e to the as this infinite sum k equals 0 to infinity t to the k over k factorial. That's multiplying the kth power of a. By convention, 0th power of any square matrix is identity matrix. Then this equals, so let's rewrite the same summation, this time in terms of the Jordan form of a. tk k factorial. And what we do is we replace a with its Jordan form, p inverse j p raised to the power k. Where we use like that a equals p inverse j. J is the Jordan drawn form. Okay. Now that equals, remember that this matrix raised to the power k simply equals p inverse times j raised to the power k times p. Okay. Just write this matrix k many times. Here you have p and p inverse, and then the next one you have p and p inverse. All those p and p inverses will cancel out, and you will have k many j's multiplying each other. Here we have a p inverse, and on the very right hand side we have a p. Therefore, this equals p inverse times j to the k times p. So let's do that. Let's write that. K equals 0, 3, tk over k factorial p inverse j raised to the power k times p. Okay. This is just a scalar, and p inverse and p, they're independent of k summation. Therefore, we can take it outside summation. What I'm trying to say is this: we can write this equals p inverse times k equals 0 to infinity tk k factorial j to the k times p. And then just forget these p's for an instant. What we have here is no other than, just look at this expression, no other than e to the jt, the matrix exponential corresponding to Jordan form. Okay, this equals p inverse times e to the jt times p. Therefore, if j is the Jordan form of A, where two matrices are linked to one another through that transformation matrix P, then e to the at must equal p inverse times matrix exponential corresponding to the Jordan form times p. So let's rewrite that. E to the at equals p inverse e to the jt times p. Remember, J was a block diagonal matrix with blocks being called J1, J2 up to JL. L being the number of linearly independent eigenvectors of A. Because of the block diagonal form of J, e to the jt will inherit that form, and in the diagonals, in the diagonal entries, we'll have e to the jit. Okay, smaller matrix exponentials corresponding to individual blocks of the Jordan matrix. Okay, so that equals p inverse that form e to the j1t, e to the j2t, e to the jlt. Okay, where matrix J is block diagonal with entries j1, j2 up to jl. Okay, now let's take an arbitrary Jordan block. Let's call it Ji. Ji had this form. Remember, lambda I 1 0 0 0 lambda I 1 0 0 0 lambda I 0 0 0. Okay. that's the form of a Jordan block. This is square matrix. Now, when the matrix has such a form, its state or its matrix exponential can be easily written down. We can write it down without derivation, but it will be easy to check whether what we will have written down is correct or not. Now it turns out that e to the ji t, where ji is the ith Jordan block of our Jordan matrix and has this very special structure. On the diagonal, main diagonal, we have lambda i's. Lambda I is one of the eigenvalues of the A matrix, and on the subdiagonal we have ones, and all the remaining entries are they are 0. Now, e to the ji t turns out to equal this scalar e to the lambda I t multiplying this matrix of very special structure. Okay, 1 t squared over 2 t cubed over 3, and so on. Then we have 0, 1 t squared over 2 factors. So everything is shifted 1 unit to the right, and so on. 0, 0, 1 t 0, 0, 0, 1. Okay. And so on. This, of course, is of the same size as ji. Now, we didn't derive this, we directly wrote it down, but it's easy to check whether this is true or not. All we have to do is to check that this matrix exponential satisfies two conditions. That it should satisfy. One condition is the initial condition constraint, that is at t equals 0, it must give us the identity matrix, which it clearly does. Okay? On the diagonal we have ones, and all the terms are t to the something. Therefore, at t equals 0, they become 0, and we have identity matrix. So that's easy. Other thing that we should check is that, so this is 1 at t equals 0. The other thing that we should check is this time derivative of this must equal ji, okay, this matrix times e to the ji t. So verify equation 1 and equation 1 by showing the two properties that the matrix exponential should satisfy for a given square matrix. First, the initial condition constraint at t equals 0. This must equal identity, which is obvious. The second thing, which requires a little bit of work, is that it solves the differential equation. Time derivative of e to ji t equals ji times e to the ji t. Okay. These two conditions are satisfied, then e to ji t must be this, because it's unique. The solution to this equation is unique. Okay. Now, by looking at 1, so that's e to ji t, and e to the jt has all these terms, e to the jit's appearing as diagonal terms. We can now reach conclusions regarding the behavior of e to the jt. easily use the following. Suppose that the real parts of all eigenvalues are strictly negative. Okay? For all I, then e to the jit goes to 0 as t goes to infinity for all I. Why is that? Okay, this e to jit, if real part of lambda I is strictly negative, then e to the lambda I t, even if it's not a real number, but it's a complex number, it will converge to 0, okay, exponentially. If lambda is purely real, then it's converging like that. If it has also some non-zero imaginary part, then it's converging by making oscillation. But nevertheless, it's always converging to 0 exponentially. And then, if the plot is 2 by 2 or larger, that means we will have some t squared, t cubed such terms. And as time goes on, as t goes to infinity, these terms are blowing up, okay, in a polynomial fashion. So here we have polynomial increase, and here we have exponential decrease. Clearly, exponential decrease will dominate polynomial increase. And under this condition, therefore, all the blocks of the state transition matrix of the Jordan matrix will converge to 0. As a result, the Jordan e to the jt will converge to 0, and then as a result, e to the at will converge to 0. And that implies e to the jt will converge to 0 as t goes to 0. And from that, we have e to the at converge to 0 as t goes to equals e to the jt sandwiched between two constant matrices. Jt times t. Okay. This is the relation between the convergence behavior and the position of the eigenvalues of the eigenvalues. Now, consider the following case. Suppose that real parts of the eigenvalues A are non-positive. Okay, they are either negative or 0 for all I, and the size of the Jordan block J, let's call index n, Jn, is 1 by 1. Whenever the corresponding eigenvalue is on the imaginary axis. In other words, when the real part of lambda n equals 0. Then all e to the jit remain bound. And as a result, e to the jt remains bounded, and as a result, e to the at remains bounded. Okay. Now, why this 1 by 1 size condition is important? It's important because if the size is 1 by 1, then we only have this thing. Okay, the block is just a scalar, and each lambda it is just oscillating with unity magnitude. Okay. Because if lambda I is purely imaginary, then the magnitude of lambda I t is 1 always. Therefore, what we have is a bounded block. If, however, the size is, let's say, 2 by 2 or larger, for the 2 by 2 case, we have here a t term. T means polynomial increase. This time, since this is purely imaginary, magnitude is always 1. It's not decreasing. Therefore, it cannot suppress the polynomial increase of that t term. That means the corresponding block, which is size 2 by 2 or 3 by 3 and so on, will become unbounded. And that means eventually the t becomes unbounded. Hence, this size constraint is important for bounding this. And finally, third case, suppose there exists some I such that, suppose there exists an index such that either of one of the following conditions hold. Okay, A, you have an eigenvalue, the A matrix has an eigenvalue on the open right half plane with a strictly positive real part, or the case that we just discussed here appears. That is, the real part is 0, that is, it's only imaginary axis, but the corresponding, the size of the corresponding Jordan blocks is 2 by 2 or larger. And size of the corresponding Jordan block is 2 by 2 or larger. Then e to the JIT, okay, that block becomes unbounded, and as a result, e to the AT becomes unbounded. Then e to the JIT is unbounded, which implies that e to the AT is unbounded. Okay, now for comparison purposes, let's recall quickly the discrete time version of these boundedness, unboundedness, and convergence conditions. So that we have the whole picture in front of us. We call the discrete time version of these conditions. Okay. Now, the discrete time version of first case one is if all the eigenvalues are with strictly less than 1 magnitude for all I. Okay. Under this condition, the state transition matrix in discrete time, which is simply A to the K, converges to 0. Okay, so this is the discrete time version of condition 2. Okay, lambda I less than or equal to 1. The magnitude is 1 or smaller for all I, and whenever you have eigenvalue, okay, on the unit circle, corresponding Jordan blocks size must be 1 by 1. Size Jn is 1 by 1. Okay. So under this condition, AK is bounded. And finally, the dt version of case 3 is the following. Either we have an eigenvalue That's outside the unit circle for some I. Or you have an eigenvalue on the unit circle, okay? That is, it has magnitude 1, and the size of the corresponding Jordan block is 2 by 2 or larger, or somehow. Okay. Either this holds or that holds, then this applies the cross-state transition matrix is moving up, it's not that. Okay, so these are, once again, the discrete time mergings of continuous time conditions that we obtain in this lecture.